Hello everyone. Today I'm going to talk about distributed and scalable electromechanical actuation for Agile systems. My name is Bonhyun Koo. I'm working with Professor Arijit Banerjee and some undergrad students. So today I'm going to go over the background and the proposed design and how to control the systems and system architecture and future works needs to be done. So as a background, this is an example from MIT Cheetah 2. As you guys can see, the movement is very stiff, and movement is very stiff. And if this Cheetah robot had a spine structure so that it can move left or right more efficiently, it'll have more dynamic movements over its movement. And another example is Atlas from Boston Dynamics. They do backflip, but this robot also has very stiff body structure. So if this system has the spine structure that can make S shape or left or right or front or back side, it'll spin a lot faster than this, like figure skating. So this is the background why I'm doing the electromechanical system for the Agile robotics. So for example, in Cheetah, the red dot is the top side of the spine is closed, and for the green dots, green spine structures, for the red spine structures, the bottom side is closed, and for the green spine structures, top side is closed so that it can make S shape or whatever it wants to run faster. And Snake also has very similar structure. So proposed architecture is that the stacks of E-cores, for now, E-cores, and for one core, there's 2 coils for each side. So in here, if the bottom side is excited, it'll be closed. And if the top side is excited, it'll close to this way so that it can make S shape, for example. And what makes it move left or right in this system is electromechanical force that is induced by the current here. So n is number of turns, which is fixed. The only controllable parameter is current here, and there's another parameter that makes the system makes the force different is gap difference, because the gap changes as I move. So to get same force, if the gap is increased, I should put larger amount of current to get the same force. And one interesting point of this system is that it can share all the one flux path. For example, ABCD is excited so that the flux goes to the right side, and for the bottom part, if this current is going up this way, so that flux path can go through the clockwise. So this excitation pattern will induce force here, and here, so that this position will be firm and this will be closed so that it'll move up. And I'm going to talk about system control. This is the block diagram of the current controller. This is PI controller, and this is system. The reason why I have R plus LS is that because of the coil with core, because R is pretty much fixed because of the coil winding, and LS. Sorry, let me make this clear. a wire, the winding, the coil with E core will have resistance and inductance usually. So that's why I have R plus LS term in here. And closed loop transfer function is this, and if I expand this, split this into two terms, it can be expressed Ki over the denominator and Kps over denominator. Kp is proportional gain for PI controller, and Ki is the integral gain. And I guess like most of you guys know about 486 control systems class. In that class, prototype second order system is the first term in here with Ki. And there's another term in this system, Kps, with the denominator here. Just the reason why I'm usually most of the all the books and papers are talking about this system, because this prototype system, because it is easy to design in terms of overshoot and rise time. It can be like easily calculated. But like the reason why I need to consider this term is that my inductance changes as the gap changes. So that if I use this controller, the current will not exceed the limit that I set. So this is the comparison between the prototype second order system and the actual system that combines all of them. So so prototype system is the design is very easy and very straightforward, but as you guys can see, the rise time is different and the overshoot is a lot different as well. So I worked on the this is the second order system design. So this is closed loop, and this is the prototype design, so that MP is overshoot value and TR is rise time from 0 to 1. From 0 to the time to reach from 0 to the steady state value, which is 1 in here. So from that, KP and KI can be like easily calculated, but in actual system, it is a lot more complicated. So I used Laplace transform to make from frequency domain to time domain. So this is the closed loop, the whole closed loop transfer function, and TR rise time can be calculated like this, and the time at peak can be calculated like this. In this formula, it is really complicated. All MP, the maximum, the peak value, the overshoot value, and all the variables are interconnected. So TP, if I put TP, I can calculate MP. Yeah, since this system is all the parameters are interconnected, the variables I set is lateral frequency, which is omega n, and zeta, which is damping ratio, so that I can, in that case, so that I can get the rise time and peak values if I put this time into the like time domain system, the system in time domain. So in this case, there's no direct way to there's no like straightforward way to calculate Kp and Ki. So to decide which Kp and Ki I need is that deciding omega n and damping ratio, which is delta. So this is the whole system architecture. This is E coil and one core and two coils. Each cell will have two current sensors for each side, and there's a potentiometer on the joint, because the reason why I put potentiometer on the joint is that I want to know which angle, I want to know the position of each cells, so that I can calculate the angle, and from that I can calculate how much Kp and Ki I will need, because Kp and Ki should be changed for different system. So this is the whole control architecture. The theta reference is that the position I want, and from here I can calculate the speed, and from this speed, if I move it fast, I should put reference value of speed, and then compare that from these two omega and theta value, I can calculate the force I need and the current I need, and from this block diagram, the reference current value will be calculated, and then the PI controller for current control is attached, so that the system, I can control the system, how fast it moves and where it goes. This is the current system, which is very messy now because I'm using 464 boards for ease of implementation. I'm only using the switch side, which is half-bridge switches. So now I'm controlling 6 coils. So I have six power electronics boards and 2 current sensors, and because only 2 coils are controlled for now, and microcontroller and OPM for position sensor, potentiometer, because like potentiometer has very small degree of angle because of the limited gap. So what I did was designing a simple differential OP amplifier so that the value varies from 0 to 3.3 volt, which is for ADC. So now this is bulky and messy system. So I'm planning to mounting all the system for each cells. So each cell will include switches and power supply circuit, and gate drivers and sensors, which include current sensor and position sensor, and eventually microcontroller will be embedded as well. So this is the multiple cells that I'm working on now, and I'm going to show you how it makes moves. So this video is step by step. I excite the top coils first, so that the bottom coils will need smaller current to move left or right. And I'm going to show you the full swing. The left side of the coils are excited at the same time, and after that, right side of the coils are excited at the same time. So as you guys can see here, the gap changes a lot. So the inductance changes varies, for example, from 5 millihenry to 9 millihenry for each cell. So the work that I need is system dynamics with adaptive control, because as I said, Kp and Ki should be adjusted as it moves. And now the system is bulky and messy, so I'm gonna design PCB for the combined system. And position and speed control should be implemented to fix to certain positions so that it doesn't fly away or move the direction that I don't want. So this is all I have today, and I'm open to questions.
Could you go back to the slide where you show the flux path?
Yeah.
Could you explain, is there a reason why you wanted to go like an additional loop where you activate 2 coils, the D and G3?
D and G3?
Is there any reason why you wanted to, instead of
just going to the middle?
Instead of ending it like ABC and that's it?
Instead of ending it ABC, because if I do this, I can firm this position.
So
Mhm.
If you want to hold it in a neutral position, you have to activate both coils.
Yeah. Because if I don't excite these coils, it'll go whatever it
It'll be loose,
moves.
right?
Yeah. If it moves, it'll move as well. So if I want this structure to be firm as I want, then I should excite both of the coils.
Have you considered maybe placing springs between in the gap so that at neutral position it just kind of remains there?
Kind of like certain basic position is there, you mean?
Yeah, some
Mhm.
just maybe
Mhm.
some springs in there,
Yeah,
or
yeah.
maybe a spring in the
Yeah.
in the joint. It's just a guess that maybe that could help smoothen out the movement as well, because just now when you're moving, it seems kind of jerky as well.
Yeah, it can help the like smooth movement, but at the same time it'll disturb my movement because I will need more currents to make it move a lot. Does that make sense? Yeah.
Well, part of it though is you need current running all the time, then to just keep it in a stable position as opposed to no current in a neutral position. So I mean, there's trade-offs, right? I mean, basically you got to have it on all the time, then just to be in what would be a neutral position, not using any current.
But like keeping neutral position is impossible, I think, without current, because there's air gap in this system now, so it'll fly away whatever it'll move like whatever the whole system moves. So the current should be excited to firm that position.
I mean, you're saying if you put springs there, then you maybe wouldn't need to use current to maintain.
Or at least use less, so that your current use would be just to correct differences from the neutral position instead of maintaining it all the time as well.
I'm just saying, in general, in engineering, there's lots of applications where you don't want to have to run power all the time to keep something in a neutral position. And I mean, maybe that's not the case for a robot, but you could use this for other things than just simply a straight robot. Right?
That is right, but like putting spring in there is trade-off, as I answered to you now. Yeah, that is right.
And a question, how do you choose to use a potentiometer to measure position as opposed to any other number of sensors that could be possible?
Yeah, so the numbers I'm getting is I measure the angle, which is negative. I set left side to be -6, because that is actual number, and right side to be 6 degree, so that it varies from -6. Neutral point is 0, and right side is 6 degree. So I'm able to measuring that, and now I'm working on the like confirming the position I want in the system.
Would it be possible to like use like optical encoder or Hall effect sensor or something? Like it seems like there are other options. Potentiometer, you'll always have to be pushing current through it and losing power to read your position. So I guess I'm just wondering if there's a lower power way of doing it.
Well, so that
I'm using low power because the potentiometer I'm using is connected to 3.3 volt, and the whole resistance is 10K, so current is really small.
Okay.
And the reason why I chose potentiometer is really small and cheap, so that I can easily mount on the system.
So are you actually using the angles between 0 to 6 degrees for your controls, or are you just using it to know if it has gone to one side or the other side?
I just using it to get the information of the position, like if that is 6 degree, or -6 degree, or
so you do
between
not
them.
actually care to know if it's between 0 and -6 degrees.
I know that value as well.
Do you need that value?
Yeah, I need that value because for maybe later, for some case, I will need to confirm. I'll need to firm a position like let me see. This is neutral, and maybe later I'll need to set position like this, which is 1 millimeter here, and which is like 3 millimeter here. Does that make sense? Yeah.
And on the topic of your e-course, why is the center roughly double the size?
Okay, yeah, the center.
Same flux.
So you mean this size is double of this, right? So it is because I use like simple equal available in the lab. Yeah, that is just yeah. This is just for starting experiment.
Question. So in your controls, you use PI controllers,
Mhm.
and you have KP and KI. What is the sign of KI and KP?
It is positive.
All positive.
Mhm.
Okay, so you wouldn't see any problem. Because I'm just curious, have you ever seen, like when you make a slab command, and because you introduce a zero to the system,
Mhm.
and at first it will the opposite to
Mhm.
your command, and then back to follow the command. Have you ever seen that?
No, I think that never happens in this system because I use positive KP and KI. Okay, thank you.